Hello guys, in this video we are going to explore numerical methods. I'm going to start a mini-series in which every 2 days I'm going to try to talk about a different numerical method and see how we can use it on a specific problem. In today's video we're going to be specifically talking about partial differential equations and how we can use them using a very simple method called finite differences. And numerical methods are really cool because with numerous advances in computer science, hardware, we can tackle some of the most complex problems that are out there. In fact, in my research, I use them on a daily basis, and I am always fascinated by the capability of computers, and also all the various methods mathematicians and researchers have came up with to solve problems using non-trivial methods. So in today's video, we're going to be talking about finite differences, and we're going to learn how to apply it to a specific problem. In this case, I chose the problem of finding the electric potential on a two-dimensional surface as pictured here. As we can see, three of the edges of the metal plate have a voltage of 0, and the top one has a voltage equal to V. And it is important to note that when dealing with differential equations, they can fall into two different categories. One is boundary value problems, and the other one is initial value problems. In the next video, we're going to tackle initial value problems because they're a little bit more involved. But boundary value problems are noted due to the fact that they're stationary. What that essentially means is that they're simpler to solve because there is no time dependency. In boundary value problems, you are given the conditions, or rather the values of our solution at the edges. In this case, we know that the voltage and the edge one and this edge and this one and this one is equal to 0, whereas the top one is equal to V. In initial value problems, you are not only given the boundary conditions, but you are also given the condition of the system at time equals 0. And then you are interested in knowing how the system evolves over time. In our case, we're simply interested in seeing how the system behaves given the constraints. In other words, we want to see how this potential V propagates throughout the metal plate. And so if you remember from electrostatics, the electric field is equal to the negative gradient of the electric potential. And in the absence of electric charges, the divergence of the electric field is equal to 0. And in this equation right here, you simply replace the electric field in terms of the potential, and you take divergence, and this gives us the Laplace operator, which is equal to 0. Now, the Laplace operator is simply the sum of the partial derivatives of x with respect to x, y, and z. Here I made a mistake, it should be z. And of course, you can express this Laplacian operator in different coordinates. In this case, it's Cartesian. And if we now take this expression and obtain its Laplacian, then we get this expression right here, which is it's quite simple. You simply take the partial with respect to x, y, and z of the electric potential to essentially get how the potential propagates throughout the metal. So in our case, this is the equation for 3 dimensions, but for simplification purposes, we're only dealing with 2 dimensions, and so we can get rid of the value with respect to z, and we get this expression right here. Now, when we are dealing with finite differences, we assume that the domain in which we are interested in finding a solution to can be discretized. In this case, imagine we were to apply a mesh over the metal plate, and so that we would have a series of little squares, which were the, the, the places where we were going to find the solution to. So if we discretize the domain, we can express the second derivative of phi with respect to x like this, and the second derivative with respect to y phi like this. And if we assume that the spacings between the different grid points is a, then we can see that as you might know from calculus, the derivative is simply the rate of change by applying some small spacing a. And so therefore we can sum these two expressions and have the overall equation for the overall finite differences equation to find the electric potential in this system right here. If we get rid of, if we combine this expression right here with expression 2, then we can get rid of the a squared and have it equal to 0. Now, in order to integrate the solution, there are a couple methods that we can use. But in this particular solution, I chose the relaxation method because the differential equation we are dealing with is relatively simple. And the relaxation method happens to be quite fast for this. Now, it is important to note that the relaxation method might not converge at the end, so due to numerical instabilities. And so for more sophisticated differential equations, you might use methods like Runge-Kutta methods or even some spectral methods. And in the coming videos, we will explore those techniques. Now, in order to find the solution, we simply rearrange this equation right here and solve for phi. So in order to do so, we bring these three values to the right hand side and we divide by a factor of 4. All right, and how does the relaxation method work? Well, in the relaxation method, you begin with some initial guess, because let's remind ourselves that we already know the solution at the boundaries. We are only interested in finding the solution inside the system. And so the approach is initially having a guess for those initial values inside the boundaries, and then apply the equations. After applying the equations, this equation right here, we take the difference between the values we obtained and some initial difference delta. To be more specific, we begin with some random numbers, then we apply this equation right here, and we get a second set of numbers that's hopefully closer to the actual solution. Now we take the difference between the new values and the old values, and we call that delta. Now, if that delta is smaller than or equal to some accuracy limit that we want to target, then we can say that our solution has converged. This approximation method is called the Jacobi method, and because we are initializing with some random guess and due to time constraints, we are setting some target accuracy, then the best we can hope to obtain is a very good approximation of the actual solution, not the actual solution. And so now let's dig into our solution using Python. And here, first I began by importing the dependencies. For this problem, we only need NumPy and Matplotlib. And these are some parameters that I set. I assumed that there would be spacing starting from 0 to 100, or 101 if we count the endings and the startings as well. Now I set the voltage to be equal to 1, and we are going to stop our relaxation method loop once we have reached a target accuracy of 1 times 10 to the negative 6. Now, the first thing we have to do is to initialize some values for phi, and this essentially creates our grid, because it creates a two-dimensional NumPy array with that's 100 by 100, and it's filled by zeros. Now we apply the given boundary condition, which is setting the top row of phi to be equal to the voltage, in this case 1, and then we apply we initialize a second dummy two-dimensional NumPy array to hold the values as we calculate them, because remember that we're going to have two sets of values. We're going to have the old solution and the new solution, and we're going to use this dummy array to hold the new solution and compare with the old solution, which is going to be stored in phi. And at the end of the loop, we're simply going to swap the numbers. So to start the iteration, we assume that the difference between the phi prime and phi is equal to 1. And here, as we can see, we have a while loop, and we're going to say that while this difference is greater than the target accuracy, then we're going to loop over all the values in our two-dimensional NumPy array. And in this if statement, we simply check if our indices, or the grid point we're considering, is at the boundaries. And if so, we simply set the new dummy value phi prime to be equal to the old value, because it's already equal to 0, which is a given boundary condition. Now, if this grid point is inside our grid, inside of the boundaries, then we apply the equation we derived previously, this one. And as you can see, it's pretty simple. And notice that we assume that there's a grid spacing of 1, and interestingly, the domain size m doesn't come into the equation. It's pretty straightforward. You simply have the phi values, and you assume a to be equal to 1, and as you can see, is exactly the equation from right here. Now, after you have completed one iteration over the entire grid, you evaluate what's the new delta. In order to do so, we utilize a method called np.max, which takes the maximum value of some list. In this case, we take the absolute difference, the absolute value between the array phi and the new set of values phi prime. Now we have to take the absolute value because phi is initialized to 0, and phi prime is going to give us a negative value since it's non-zero values. Remember that initially phi prime is equal to np.empty, and what that essentially creates is a two-dimensional array of size n plus 1 by n plus 1, and it initializes to some random values. As we can see here, you simply pass in the dimensions of the NumPy array, and it gives you some random values inside. So we have to take the absolute difference just in case this value is less than 0, and then you simply take the maximum value of that. At the end, you simply swap the values so that the new phi corresponds to phi prime, and the old phi prime corresponds to the old value of phi. So in the next iteration, the new solution phi prime is going to serve as the old solution for comparison when calculating the delta. And at the end, we can simply plot it using the mshow method from matplotlib. In this case, we chose a color map to be of magma, and this is the solution that we end up getting. As we can see, it's pretty cool how the potential propagates throughout the metal. We begin with this, we apply some voltage, and after we apply the voltage, we can see how it propagates. On the top, it's going to be equal to 1. at the top is going to be equal to 1, and as it goes down, the voltage begins to decrease gradually. And because this is a stationary equation, it does not change with time, and thus um, on the bottom, we're not going to have any voltage at all. Okay, so this is the video for today, guys. I hope you liked it and found it useful. In the next video, I'm going to tackle the same problem, but I'm going to assume that there are some positive and negative charges, and we're going to see how it affects how the manner in which the voltage propagates throughout the metal plate. Moreover, if you have any questions, or is there any numerical method you would like me to explain, please let me know in the comments, and don't forget to subscribe